Hello everyone, welcome again to Modeling Methods in Mechanical Engineering, and today we're going to continue with introducing the concept of field theory and the different operations, vector operations that we can do. In last class we had actually talked about the gradient and what it means and how we can actually figure out from the gradient of a scalar function. And let's kind of recast that. So modeling methods in mechanical engineering. Let's just recast the concept of the gradient, which means that the gradient of a function, which we can short notate as nabla f, we can read this as del f, is in fact, in Cartesian coordinates at least, the derivative of f with respect to x in the x direction, the derivative of f with respect to y in the y direction, and the derivative of f with respect to z in the z direction. So we turn a scalar function f into a vector. And that's what the gradient does. Okay, now in follow-up lectures we'll see that we can extend this to another order, and if the field function f is actually a vector, then the gradient operation will turn it into a tensor, but that's a little bit more advanced. So one property of the gradient is that the gradient of a function is always perpendicular to its level curves. And we had introduced this concept of level curves, and so, for example, given z equals f of x and y, so that z equals c, define the level curves. And let's say that these function f of x and y, when we project into the xy plane, we had shown, for example, these hyperbolic paraboloid where we had the following. So the level curves of the function f, if it's a hyperbolic paraboloid, would look something like this. What we call the isocontours of f. So this is f of x and y projected into the xy plane. So sort of like the function seen from the top. The gradient of that function will always be something that points perpendicular to this line. So it would go sort of like this. Sort of like this. So it will always be perpendicular to this line. So the red lines are perpendicular to the blue lines, and in addition, the red line has a specific direction. Maybe up, maybe down, depending on what the vector field looks like. And just do it like this, and then one in this direction. So because remember, the gradient, such that this is the gradient of f, and remember the gradient of f is a vector field, and the vector field has their vectors, and therefore they have directions, not only magnitudes. So at every point you have a vector pointing in a specific direction that is perpendicular to the blue line with a specific magnitude. So we can use this particular property to define a unit normal vector to any set of level curves or 3D surfaces. So again, if f of x and y defines a surface, whether it's a 3D or higher dimensional surface, then n, the normal vector to that surface, will be the gradient of f divided by the magnitude of the gradient of f, such that n is the unit normal vector to surface f. And it's unit because we're dividing, notice, we're dividing by the magnitude of the gradient of f. So gradient of f defines a direction which is perpendicular to the level curves of f itself, and by dividing by the magnitude of that direction we come up with a unit normal vector. So not only this vector is normal to the surface of that's defined by f, it is also unit in length because we're dividing by its own magnitude. All right, so let's do an example. Let's say that we have a cone, the cone c squared minus x squared minus y squared is equal to 0. And if we try to plot these into the xyz plane, the cone, this conical function would look like this. It basically defines a surface around this cone, and obviously it would propagate up forever. It doesn't stop right there. That's just the intersection of that cone with a particular value, constant value of z. But these cones will actually propagate forever. And if we want to know at any particular point on the surface of this cone, let's say here, so that's a particular point on the surface of the cone, there's a normal vector that points perpendicular to that surface and is unit in length, and we call n. If we want to find what are the coordinates of n, we define f of x, y, and z equals to a constant. So we define the level curves such that f of x, y, and z is equal to, so we make these particular relation equal to a constant. It's already equal to a constant. 0 is a constant, but we can make it equal to any other constant we want, and the result will not change. So we can make it equal, we can make this c squared minus x squared minus y squared plus 5, and that's still equal to a constant because this is equal to 0. So it really doesn't matter. So we can say or f of x and y and z is equal to z squared minus x squared minus y squared plus 1. We can also make everything negative. It really doesn't make a difference, right? Because they're still equal to a constant. If the function is defined by these, the cone, the surface of the cone is defined by z squared minus x squared minus y squared equal to 0, anything that equals a constant is actually a valid proposition for a function whose level curve define the surface. So the normal vector to the surface should be the gradient of the level curves divided by the magnitude of the gradient of the level curve, such that the gradient of f, remember, is equal to df dx in the x direction plus df dy in the y direction plus df dz in the z direction. So the gradient of f, I'm going to do this in one shot. I'm going to basically take the derivative of these with respect to x, and that will be minus 2x. the derivative of these with respect to y, it's minus 2y. The derivative of all these with respect to z is plus 2z. And you can see why there wouldn't be any difference if you add or subtract a constant. There'll still be a level curve, there'll still be a constant, and you'll get exactly the same results, right? And therefore, the magnitude of these is equal to the square root of minus 2x squared plus minus 2y squared plus 2z squared. And when we take care of these, we can take the 2 as a common factor, and that will be x squared plus y squared plus z squared. Leading up to the normal vector, which is this one divided by this, is minus x. And I can actually take the denominator and spread it over every term so that it is clear what's happening here. In the x direction, minus y divided by x squared plus y squared plus z squared. In the y direction, plus z divided by the square root of x squared plus y squared plus z squared in the z direction. So I could take that denominator and just place it outside as a common factor, do a parenthesis, and the vector will just basically be minus x divided minus x in the x direction, minus y in the y direction, and z in the z direction. And notice that's a vector field, right? And then all that multiplying a common factor of 1 over the square root of x squared plus y squared plus z squared, where every one of the components is as I write them on this form right here, this expression. And you can figure out that this expression is also a vector that at any point will be unit in length, because if you square these, add these one square and add this one square and take the square root, you get exactly 1. Okay, now this vector, if you look at it, seems to be pointing in the negative x direction at a positive x point, in the negative y direction at a positive y point, and in the positive z direction at a positive z point. So if you pick a point in the positive xy plane, so this point, and in the positive z axis, so this will be like 0.111 on this cone, the normal vector seems to be pointing inwards. So why is that? Well, we could have selected a level curve that was the negative of all these, because the negative of all these is still equal to a constant because it's equal to 0. So this is actually notice this is an inward drawn unit normal vector. What if we want the outward drawn unit normal vector for whatever particular application that we're working on? If we, for engineering purposes, we are always interested in the outward drawn unit normal vector. And that again is just a universal convention, because most quantities in engineering are defined as positive going out or positive leaving a control volume. So in this particular case, if we want to define the normal vector that is equal to this one but opposite in sense, all we have to do is multiply the whole thing by -1. And again, this denominator can be taken out as a common factor, but just for illustration purposes, I am just leaving it underneath every single component. So this is the same vector it just points in exactly the opposite direction as this one. All right. Now, because now we have the ability to calculate normal vectors to any surface, now we can calculate what's called the normal derivative. So we can take a function and calculate its normal derivative with respect to the normal of a particular surface by simply calculating the directional derivative in the direction of the normal vector to a surface. So the normal derivative of f, given a function f that's some field function, some field scalar, for example, we can calculate what's called the normal derivative of f, denoted dn of f or df dn in partial, and is simply equal to the gradient of f times the normal vector. Now, it is important that we do not confuse the fact that the normal vector is also calculated through a gradient, but it's the gradient of whatever actually represents the surface through which we're calculating this normal derivative. So f is an independent function of the surface that from which we get this normal vector. So let me give you an example. For instance, given the temperature distribution Tx of y. Again, we're going to do this in 2D. So a temperature distribution on a 2D plate on the surface of this table, for example. Fourier law of heat conduction states that the heat flux vector, we already defined that, Q is equal to minus K grad T. So if we know the temperature distribution on a surface or in space, we can just take the gradient, multiply times the thermal conductivity of the medium, of the conducting medium, negative sign, we get a vector that represents the energy flux or heat flux. Okay? Now, if we need to know the amount of heat entering or leaving through a surface F, then, and notice that I'm interchanging the nomenclature here, because here we're calculating the normal derivative of F. In this case, the surface is defined by F. So this is what's going to happen. So let me illustrate this first. So we have a domain. Okay, and this domain is just some volume, omega, whose surface is defined by this function f of x, y, and z. Okay. Through the surface, we have a temperature distribution. Let's see, now it's three-dimensional. And that temperature distribution induces an energy flux, which we call the heat flux, which is also a function of x, y, and z. And it's also directionally dependent for vectors. All of these lines are just piecewise vectors at every point. Right? Now, if we take a piece of the surface of the surface of omega. Omega is the volume, and let's just say that this is a piece of the surface. So this is gamma, which is part of the surface that surrounds omega. There is a normal vector n. Remember that it's defined by grad f divided by the grad of f, where f defines the surface, right? And the heat flux at that particular point, if you take these blue lines here that define the heat flux, one of them might be actually pointing like this, Q, at that particular point. Now, if we need to calculate the amount of energy leaving through this little window right here, well, we remember the heat flux vector is energy per unit time per unit area. All we need to do is multiply times the area, or integrate that heat flux over the area, but we also need to dot it into this normal vector. Okay, we need to actually calculate the projection of this flux line in the normal direction, because that's the amount, the actual effective quantity of the amount of energy leaving through this window every second. So basically, what will happen is that will be the normal heat flux, which is Qn dotted into the normal vector, such that the normal vector is equal to the gradient of f divided by the magnitude of the gradient of f. So, therefore, Qn is equal, remember that Q is defined as minus K grad T, and then that's Q, and then this dotted into N. So therefore Qn is equal to minus K grad T dot N, and this is nothing but the normal derivative of the temperature. So the normal heat flux is minus K times the normal derivative of the temperature at a normal point, normal to the surface, at a point normal to the surface of this region. Okay, so this is just an illustration of how this concept of normal derivative will be used. The amount of heat flux, and this still in units of watts per meter square. If we want to calculate the energy rate, Q, then we will have to multiply Qn times whatever area, surface area. And this will lead to units of watts, energy rate, or power leaving through that surface. The amount of energy leaving through the surface per second. All right. So let's look at another concept. And that is the concept of the tangential derivative. So now we know that we can calculate the normal derivative by basically calculating a directional derivative in a normal direction to a surface. The tangential derivative is the directional derivative in the direction of the tangent vector to a surface defined by a set of level curves, or 3D surface. So essentially, if we have the tangential derivative denoted as ds of f, of a function f, is the gradient of f dotted into the tangential vector, which is also denoted as df ds. Well, in 2D, if we have a surface in 2D, this is omega, and again this will be gamma, which is d omega, so essentially a piece of the surface defining omega. And again, let's say that we have f circulating in here, f of x and y, and this is a 2D. So we have some sort of f doesn't define the region. F is just some scalar field that is valid within that region, and we want to calculate the derivative of that field, maybe the temperature, and calculate it normal to or tangential to the surface. The normal derivative at this point, the normal vector will point in that direction, and the tangential vector s will point either in this direction or in the opposite direction. Both are very valid. So you use the right-hand rule to define, well, if the normal vector has to be properly defined pointing out, then the tangential vector has to be pointing, in this case, to the right. So it depends on whether you do this counterclockwise or clockwise, depending on how you actually define the geometry. Okay. Now in this case, we can do this in 3D, but it will be slightly more complicated because in 3D, again, we have a 3D region whose surface, or a piece of the surface gamma here, is derivative of omega, and there's a unique, at the center point of that region, there's a unique normal vector n, but there's an infinite number of tangential vectors. Okay, there's an infinite number of tangential vectors to this surface. So which one do we pick to be s? Well, we have to define some convention. Is it the one that is also perpendicular to s? Well, they all have to be perpendicular to n because the tangential vector has to be perpendicular to n. But it can be defined on a local coordinate system where the tangential direction obviously perpendicular to the normal one, but satisfying some specific reference frame. In that case, it wouldn't make much sense, but again, we have internally this scalar field f that is defined throughout space that has nothing to do with the region itself. The region is actually defined by some other function. Okay, so I'm purposely interchanging the nomenclature here just to give you an idea. But at the end of the day, what we're after here is the fact that we can calculate the tangential derivative of a function f if we have a direction that is tangential to a surface, whether that surface is the surface of a 3D region or whether that surface is the line that surrounds a 2D region. If we have that tangential direction, we can calculate the directional derivative of this function f and dot it into that tangential direction or tangential unit vector and calculate the resulting tangential derivative. Okay. So let's introduce another concept that you probably already heard of, more than likely, and that is the concept of the divergency of a vector field. So now we're going to depart from the fact that we have a vector field and not a scalar field. So given a vector field, and let's define this vector field V, which is a vector and it's a function of x, y, and z. So we have a component Vx, which is a function of x, y, and z in the x direction. We have a component Vy, which is also a function of x, y, and z, and is a component of the y direction. And then we have a Vz, which is x, y, and z. Easy. Okay. we are going to use a shortcut here and just simply say that V is Vx, Vy, and Vz. These are independent components of the vector field. Each of them is an independent function of x, y, and z, potentially. Okay, this is what a vector field means. Okay. Now, what could a vector field be? Well, think of it as we're mechanical engineers, so we're going to think in terms of mechanical engineering things. So this is, think of a fluid flow. Think of a fluid flow, and V is the velocity of that fluid flow. Why is the velocity a vector field? Well, imagine the air in this room. The air in this room is actually moving, and it's moving because of buoyancy effects, because it is hotter on the ceiling than what it is on the floor. So the air is going to have a tendency to rise, and as it rises, actually goes through the walls and it circulates. So there's all kinds of things that we cannot see in this room in terms of a pattern of flow field or flow field configuration, because air is transparent to us. But if you actually had the ability to color the air in this room, you'll be able to see some very interesting patterns. Because natural convection, for example, in this case the driving force behind the motion of the fluid in this room, actually produce very interesting patterns. So at every point in space in this room, we can pick, at every point in space, I'm sorry, there was a glitch on the recording. At every point in space, right here, we can actually visualize the flow field and see that the flow field not only has a different value than a point right next to it. Okay, so this is point x1, y1, z1. This is point x2, y2, z2. And the two vectors of flow field have a different value, different magnitude, different direction, because the flow field might actually be curving up or doing something. Okay, so we have a different value here and here. Not only that, well, we can tell it's a field because we have a functional distribution of the velocity field around, but at every point, the vector field, or the field, is defined by three directions. The vector field is pointing, so it has a direction, and it has a magnitude. It has a quantity that defines its magnitude. All right, so we can calculate the divergency of V, and think of V again as a velocity field of a fluid flow, as the limit when omega goes to 0. And remember, we're using omega to define a region in space, normally 3D, but it can be 1D or 2D. As omega goes to 0 of 1 over omega, the integral around the surface of omega of B dot n, the gamma. And you've probably never seen the divergency written this way. You're probably used to seeing the divergency of some kind of vector differential operator, right, where you take the divergency of certain things, the derivative of certain things. But by definition, this is what the divergency is. The divergency is an actual integral operator, but when the limit of the region over which you're integrating goes to 0. Okay? If you remember from your calculus 3, this is a surface integral, and this is a surface gamma that surrounds omega. Okay? So this is what's called a scalar operator. We're taking a vector field, which is a vector. We're dotting it into a normal vector to some region. That will make it a scalar, because this is a dot product. So the resulting, or the divergency, will result in a scalar. Okay, a function, but it's a scalar. So if we want to visualize what this means, think of, again, the region omega, okay, which might be defined by some function f. And this is the surface of the region omega, we call it gamma, right here. We have a piece of that surface, a differential of gamma. That's what is exemplified here in this integral. And crossing that region, we have a vector field, and it has pointy arrows because it is a vector field. So this is V. So the vector field V is actually traversing that space. Right at this particular point on the surface, the differential surface, we have a normal vector. And the velocity field, if we follow these arrows, might actually be pointing in a slightly different direction than the vector field. And V dot n is essentially the projection of V into n. It's essentially taking the magnitude of V into the direction of n times the sine of the angle that separates the two. Okay, so the cosine of the angle that separates the two. That's the inner product. So if the velocity and the normal vector point in the same direction, the V dot n actually results exactly in the remember that the magnitude of n is equal to 1, so the length of n is equal to 1. So V dot n, if they're both in the same direction, V dot n will be exactly the magnitude of V. If they're perpendicular to each other, there is no fluid escaping through that little window, right? So this quantity right here gives you the effective amount of fluid escaping through that little window. If it goes perfectly perpendicular to the surface, all of it escapes. If it goes somehow tangential to the surface, then none of it escapes. Anything in between is by the cosine of the angle, and that's what V dot n is. It's essentially the magnitude of these times the magnitude of these, which is 1, times the cosine of the angle in between. Okay, that is the projection of one vector into another. All right, so what does this integral mean? Well, we're going to do that. We're going to take that V dot n, which is the amount of velocity escaping through this little window. Then we're going to multiply times that surface area. What is velocity times area? That's flow rate, right? Velocity times area is volumetric flow rate, meter cubed per second. Remember, velocity is in meters per second. The normal vector has no units. And the derivative of gamma is just represents a piece of the surface which has units meter square. So this is meters per second times meter square, then that is meter cubed per second. When we integrate over the entire surface, we're basically accounting for, we're taking this particular window and replicating it all around the surface that surrounds this region. So we're basically calculating the amount of fluid going into the control volume and leaving the control volume instantaneously at the same instant in time. We're calculating at a particular instant in time the amount of volume that actually enters and leaves this control volume, the amount of flow that enters and leaves the control volume. If that number is equal to 0, it means that the flow is incompressible. There's no way to stretch the flow or compress the flow because whatever goes in equals whatever goes out. We know this from fluid mechanics. An incompressible flow will mean that whatever goes into a control volume leaves the control volume instantly on the other end. Okay? Now, if there was some compressibility to this flow field, then this quantity will be different than 0. And this is what divergency tells us in the case of fluid mechanics. Okay? Divergency also has a meaning in fluid flow and heat transfer and solid mechanics, and in electricity, of course. The divergency of an electric field being equal to 0 means that the field is solenoidal. It's the same concept. It has no distensibility. So here, V is a vector field. And for illustration purposes, we are going to talk about this vector field as being a velocity field. That's why we use V for it. Omega is the volume or domain. Could be 1D, 2D, or 3D. In this case, it's 3D. Now, if the volume omega is 3D, then the surrounding surface is 2D. So the surface that surrounds a region, gamma that surrounds a region, is called d omega because it's usually it's always one dimension lower than the volume itself. Surface or boundary of omega. All right. Now, as I mentioned, this is not a form that you might be familiar with. You might have never seen the divergency defined in this particular way, but we're going to apply some tricks here to actually make it look like you're used to. And because this is a graduate course, I'm not just going to give you the answer of what is the final form of the divergency. We're going to figure it out. So in order to do so, we're going to use a very old trick that comes in handy on pretty much every situation. And where you take this omega and we're going to make it a small rectangular infinitesimal region. So every time you want to figure out what these very complicated forms look like, you make it small and you make it rectangular. That would actually make things very easy to do. So omega is just a parallelepiped of size delta x, delta y, and delta c. So if we draw the Cartesian coordinate system here, be careful the way I define this. Oops. So this is a parallelepiped of size delta y, delta x, and delta c. It starts here at the origin. All right. So we have now this parallelepiped is small and it is clearly divided into 6 surfaces. The region omega is surrounded by a surface gamma, but that surface gamma can be clearly broken up into 6 independent surfaces, basically the 6 faces of these particular parallelepiped. And the bottom of these, I'm going to use another ink here so you don't get this confused. On the bottom of these, we have a normal vector that is equal to the negative of the vector EZ, which is the vector that points in the z direction, but it's a negative of it because it points down. And then we have the velocity coming in, which is Vc. The component of the velocity, well, the velocity field is just a velocity field, but the only one that will survive when we multiply v times n is the z component of the velocity, because the normal vector points in the z direction. On the top of these, you have a normal vector that is now positive Ez, and a velocity, which is Vz plus delta z. So whatever the velocity z is, here down on this wall, plus delta z. Okay, it's not the velocity plus delta c; it's the velocity at z plus delta z. This is the velocity at z, and this is the velocity at c plus delta z. Let's look at what happens on this wall right here. The normal vector here would be minus ey, negative ey, and the velocity is the y component of the velocity by. The only one that will survive. Remember that the velocity is just some. I don't have a green ink, but the velocity field is just some velocity field that traverses this entire region that has x, y, and z components. Okay, but the only one that will survive when we multiply v dot n here, when we do the integral along this face, is the y component, because the normal vector, you only have the y component. And here, the normal vector is equal to ey, positive, so a vector that points in the y direction. And where do I do this? I'm going to do it here. This is the velocity at y plus delta y. Okay. And likewise, in the back wall here, we're going to have a normal vector, n, that is equal to minus ex, and we're going to have a velocity that is vx. That's the only one that's going to survive. And I'm sorry, the vx points inwards in the direction of x. Okay, let's just make it point that direction. It actually doesn't point because it's just a component of the vector. Every component of the vector is a scalar. And in here, the normal vector is minus Ex. And the velocity field is Vx plus delta x. All right. Now, given Vx, the component Vx, what is Vx plus delta x? Again, it's not Vx plus delta x, it's V at x plus delta x. What is that? So, in order to do that, anytime we want to expand the value of some function at any particular point, we use the trick of a Taylor series. And what the Taylor series will give us is Vx plus delta x is equal to Vx plus dvx dx times delta x plus 1 over 2 factorial, the second derivative of Vx dx squared times delta x squared plus 1 over 3 factorial, the third derivative of Vx dx cubed delta x cubed plus, it's an infinite series. Okay, this is what a Taylor series does. Okay, now because delta x is small, then delta x squared is much smaller than delta x, and delta x cubed is much smaller than delta x, and so on and so forth. So we can approximate Vx plus delta x as Vx plus the derivative of Vx with respect to x times delta x. And again, this is an approximation, but it's a really good approximation. It's a first order approximation because delta x is small. It will cease to be an approximation. It will become exact because we'll make delta x equal 0. Remember that we're trying to take the limit in which this region goes to 0. So we'll make this infinitesimally small, dx, and therefore this approximation will no longer be an approximation, will be exact. Okay. Now similarly, we can do exactly the same with the other components. Similarly, Vy plus delta y should be approximately Vy plus dvy dy times delta y, and Vc plus at z plus delta z should be approximately Vz plus dvz dc plus delta c. All right, so we are trying to figure out how to express these in a way that we can actually operate this expression for the definition of the divergence. And for it, we need to calculate this total surface derivative. Total surface integral. This is a surface integral. This is a closed contour surface integral over the entire region omega surrounded by the surface gamma. So the integral over the entire surface of v dot n d gamma should be equal to the integral of, on the left wall, of v dot n d gamma plus the integral over the right wall of v dot n d gamma plus the integral over the bottom wall v dot n d gamma plus there are 6 of these, the integral over the back wall v dot n d gamma. Okay, so basically we have to calculate 6 of these integrals. Now if we look at v dot n and we look at every one of these walls, let's say for example the front wall right here, v is vx plus delta x, n is minus ex, so this one times this one is minus vx plus delta x. Okay, this one times this one is, because of the minus sign, is minus vx plus delta x. So we can essentially take this entire integral of v dot n over the 6 faces of this parallelogram or parallel pipe. And on the left we have Vy, the normal vector is -1, and d gamma, we're going to talk about the left wall, it's this wall right here. D gamma is the area of this wall, and the area of this wall is dx, or delta x times delta z. Delta x times delta z. Plus Vy plus delta y, that's on the other side, on the right hand side, times the normal vector, which is 1, delta x delta z. The area of the wall on the right hand side is also delta x times delta z. So it's this region, this line, which is delta x, times this line, which is delta z. Plus Vz times -1 times delta x delta y, plus Vz plus delta z times 1 delta x plus delta y, plus Vx times -1 delta y times delta z, plus Vx plus delta x times -1 times +1, delta y times delta z. So these are the 6 different integrals approximated using the components that survive, because the normal vectors are just single component normal vectors. It's either minus EY or plus EY, minus EX or plus minus EZ or plus EZ, minus EX and plus EX. So those are the only components that survive. So I'm going to continue with these. V dot n. And this is minus Vy delta x delta z. And we already know what these Vy plus delta y, given this approximation up here, V at y plus delta y is Vy times so on and so forth. So this is going to be Vy plus dVy dy times delta y dx dc. So I'm going to continue here, minus Vz delta x delta y plus Vz plus dVz dz times delta z delta x delta y minus Vx delta x delta z plus Vx plus dVx dx, the Taylor expansion, the Taylor series expansion of these components right here, delta x, delta y, delta z. If you notice, this term right here will cancel with this term right here when it multiplies delta x and delta z. So this one and this one go away. Let me use a red ink. So this one and this one go away. Same, this one and this one will go away. And this one and this one will go away. So this integral over the entire region, given that the region is a parallel pipe of size delta x, delta y, delta z, is equal to, so notice that everything now multiplies delta x, delta y, delta z in different orders, but we can take that as a common factor. And I'm going to rearrange this as dvx dx plus dvy dy plus dvz dz, delta x, delta y, delta z. Okay, so we figure out what that integral looks like, at least on this particular rectangle, on this parallel pipe. Okay, now the divergency of the vector v is defined not as that integral, but as the limit when omega goes to 0 of 1 over omega times this integral. This integral is the integral over gamma, v dot n d gamma. Okay, now who's omega? Omega is the volume, and that volume, we said it had the size of 1, or the volume is size delta x, delta y, delta z. And this integral right here, I'm going to use brackets instead, and then this integral we already figure out is dvx dx plus dvy dy plus dvz dz, delta x, delta y, delta z. So notice that the denominator, the volume, goes with the volume on the numerator. And now the divergency of V is equal to dvx dx plus dvy dy plus dvz dz. And this is something now that might look familiar to you. If you take the divergency of a vector field, all you have to do is take each of its components, differentiate them with respect to its own direction, and add them together. And this is a scalar operator. Notice that you started with a vector field that had components ex, ey, ez, and you ended up with a scalar field that has no components. This has no components ex, ey, ez. So we can also recognize that this is equivalent to writing the divergency of V is equivalent to del dot V. And this is true in Cartesian coordinates. It is not directly true in other coordinate systems like cylindrical or spherical or so on. So that's this resulting in a scalar function. Remember, nabla is this operator that is d dx in the x direction plus d dy in the y direction plus d dz in the z direction. Okay, that by itself doesn't mean anything, but when applied to something else is a differential operator. And these dots make a world of a difference. Okay, the gradient of f is nabla f, also read as del f. So it takes a scalar function f and turns it now into a vector. So resulting in a vector field. And the divergency of a vector field is del dot v, which is something completely different. Del dot v, this results in a vector. And this results in a scalar. They're both vector operators, okay, but by definition the divergence is an actual integral operator that results in a vector operator, in a differential vector operator. The gradient takes a scalar and turns it into a vector. The divergence takes a vector and turns it into a scalar. Okay, so they modify the order of the function in which they operate completely differently. So the gradient increases the order of the function, while the divergency decreases the order of the function. Okay. So be careful with that. These are not the same thing. Del V or del F is not the same thing as del dot V. One is the gradient and the other one is the divergency. One increases the vector order, the other one decreases the vector order. It goes from vector to scalar. All right. So this was an exercise on derivation. Essentially demonstrate that the divergency has this form from the original definition of divergency, which is, well, this is the definition of divergency here. And we apply that trick of the parallel pipe and ended up with the divergency having this particular operator form. Okay, so a vector field V, whose divergency is 0, So if the divergency of V, which is the divergence equal to del dot B, happens to be 0, then is said to be incompressible or solenoidal. So incompressible when you're talking about vector fields and fluid flow, solenoidal more when you're talking about electric fields and magnetic fields. So, for example, in fluid mechanics, given V equals to U, V, and W, the three components of the velocity field. And by the way, in fluid mechanics, U, V, and W are used instead of Vx, Vy, and Vc. These are components of the velocity field. These are functions themselves, so that's why we call this a field. Recall that the velocity components, U, V, W, are functions of x, y, and z, each one independent of each other. Okay, one can be a function of x, y, and z, the other one is another function of x, y, and z, and so on. If it happens that a particular velocity field has 0 divergency, the flow is said to be incompressible. That is, by definition, the divergency of V is the derivative of the first component with respect to x plus the derivative of the second component with respect to y plus the derivative of the third component with respect to z. It's a scalar operator. There's no ex, ey, ez. They're all added together into the same term. And if that's equal to 0, then the flow field happens to be incompressible. It doesn't have to be an incompressible fluid. It doesn't have to be water or liquid. It can actually be air, which is highly compressible fluid, but it might be flowing in an incompressible manner because its divergency is equal to 0. Now, by definition, as we talked about, this is what this integral means. This integral is quantifying the amount of flow rate. The velocity times the normal vector is the effective amount of velocity leaving through every single piece of window on the surface. And when you integrate that, you're basically multiplying velocity times area all over the surface that surrounds this volume. Velocity times area is volumetric flow rate. By integrating it over an entire region, you're basically quantifying the amount that goes in and the amount that goes out instantaneously. If the amount that goes in is equal to the amount that goes out, it's basically there's no way for the flow to distend or compress, and the flow then is said to be incompressible. So when the divergence is equal to 0, the flow field is incompressible. Okay. Now on a separate note here, some consequences of these definitions of divergency and gradient and so on. Consider a scalar function phi or phi. Okay. So the scalar function could be the temperature, it can be any scalar function, it can be the potential, the gravitational potential. Actually, this is a common name for the gravitational potential. The gradient of phi, i.e. del phi or nabla phi, is a vector field. Again, if phi were the temperature, then the gradient of phi is related to the heat flux through the thermal conductivity, the negative of the thermal conductivity. If phi was the gravitational potential, then the gradient of phi would be associated with the gravitational force, okay, magnitude and direction. Okay, the divergency of the gradient of phi, i.e. the divergency of the gradient of phi. So remember, when we take the gradient of phi, we obtain a vector field, and then we can take the divergency of that vector field. That's allowed because divergency, you can only take the divergency of a vector field. You cannot take the divergency of the scalar. Now you turn it back into a scalar. Is a scalar. So let me go to another page. So the divergency of the gradient of a potential function or scalar field phi can be written as del dot grad of phi, or del phi, and the shorthand notation for these is nabla square of phi. Okay, nabla square of phi is known as the Laplace of phi. So taking the Laplace of phi is equivalent to taking the divergency of the gradient of phi. Okay, this is not the Laplace transform. This is a completely different thing, but it's also due to the same Laplace. Okay, so if we expand these in Cartesian coordinates, the divergency of the gradient of phi would be the divergency of the gradient of phi, which is the phi dx in the x direction, plus the phi dy in the y direction, plus the phi dz in the z direction. So the Laplace, or the divergency of the gradient, is equal to, so the nabla we can expand as d dx ex plus d dy ey plus d dz ez, dotted into this whole thing. So I'm going to squeeze it in here. The phi dx in the x direction plus the phi dy in the y direction plus the phi dz in the z direction. Okay. So now we have two vectors dotted into each other. The result of that operation is a scalar. So del phi should be the derivative with respect to x of the derivative with respect to x of phi, which is the second derivative of phi with respect to x squared. The ex go away because this is a scalar operation. Plus the derivative with respect to y squared of phi, plus the second derivative with respect to z squared of phi. And that we call the Laplace of phi. So the Laplace is essentially, the Laplace of a scalar is essentially taking the second derivative with respect to each of the coordinates. And that is because it is the divergency of the gradient. And this right here is the Laplace operator. Again, not to be confused with the Laplace transform. This was the basis of the entire gravitational potential thing, where phi is a gravitational potential, and then phi actually was obeyed the Laplace equation, which is the Laplace of phi equals 0. Okay, note that the divergency of the gradient of phi is not the same as the gradient of the divergency of phi. In fact, this operation here is not allowed because you cannot take the divergency of a scalar. You need a vector to be able to take the divergency of. Okay? Also, we can say that a function phi, which is normally called a potential function, whose Laplace is 0, is said to be harmonic. So if the Laplace of phi is equal to 0, then phi is harmonic. If the Laplace of phi is equal to 0, then phi is a harmonic function. Okay? So that's where we end up today. That's where we finish the class today. By the way, this Laplace is an operator that, notice, actually let me write that. So we can also take the Laplace of a vector field. So in here we're taking the Laplace of a scalar phi, and its derivative with respect to x, y, and z. Second derivative with respect to x, y, and z. But for example, i.e., given a vector field v, which is u in the x direction plus v in the y direction plus w in the z direction. Let's say that this is a velocity field. Okay, we could potentially take the Laplace of v, and that will be the Laplace of u in the x direction plus the Laplace of v in the y direction plus the Laplace of w in the z direction. So note that the Laplace operator keeps the tensor order of the function on which it's operating. If you take a scalar function phi and calculate its Laplace, you end up with a scalar function. You end up with the second derivative of phi with respect to x squared, plus there's no vector components here. So you start with a scalar, you end up with a scalar. You start with a scalar phi, you end up with this function, which is the Laplace of that scalar function phi, which is also scalar. If you start with a vector v that has 3 components, then you end up with a vector with 3 components, each of the components being the Laplace of the original vector, of the components of the original vector. So again, the divergency, the gradient of phi increases tensor order. And now I'm talking about tensors, and we don't even know what the tensors are, but trust me, we'll look at those. The divergency of v decreases tensor order. And the Laplace of phi maintains tensor order. What does that mean? The tensor order is essentially the following. So a vector is a tensor of order 1, one dimension, or one set of dimensions, ex, y, z. A scalar is a tensor of order 0. A tensor of order 2 is a matrix, a vector of vectors. Okay, so if you take the gradient of a scalar, you end up with a vector, with a tensor. You take the gradient of a tensor of order 0, you end up with a tensor of order 1. If you take the divergency of a tensor of order 1, which is a vector, you end up with a tensor of order 0, which is a scalar. If you take the Laplace of a tensor of order 1, which is a vector, you end up with a vector, maintains the order. If you take the Laplace of a tensor of order 0, which is a scalar, you end up with a scalar, which maintains the order. Okay? In that regards, if you take, for example, the gradient of a vector field, you could do that, but you end up with a tensor of order 2, a full tensor. If you take the divergency of a tensor, you end up with a vector because you reduce the tensor order by 1, by 1, by 1, by 1. But what's important is that the gradient, the divergency, and the Laplace are not the same thing. The gradient of phi is denoted del phi. The divergency of v is denoted del dot v. The dot makes a huge difference there in the nomenclature. And the Laplace of phi is denoted del square of phi, which is actually the divergency of the gradient of phi. And on that note, we are going to end the lecture today. So thank you for your attention, and I will see you during the live sessions or on the next online lecture. Goodbye.